Hi everyone. So today we're back with section 4.3. This is about maxima and minima. So this section is something that we should definitely pay attention to. Um, Honestly, so 4.1 that was on related rates. That was applications. It was pretty short. 4.4 was on the mean value theorem. Like I said, the important part there was kind of like the corollaries of it. Those corollaries will come back in this section a little bit. And then the last section was linear approximation and differentials. And we're really not going to see a whole lot of that now throughout the course. This, however, is very, very important. So if you're going to make sure that you know something, this is kind of the start of making sure that we're really solid on a certain topic. Because this topic could come back a little bit in Calc 2, and it's really just important to understand the ideas behind this specific topic here. So here we're just going to be talking about maxima and minima, which is just the plural of maximum and minimum. All right. So the first thing that I'll introduce is this idea of absolute extrema. I do think that I have an actual definition of that. Um, but essentially, extrema is just the combined idea of maxima and minima. So extrema are any maximums or minimums that you may find. All right, so given this parabola right here, we do have an absolute minimum. We do have a minimum, which is right here. As we can see, it's the vertex of our parabola. And it's something called the absolute minimum. We will introduce formal definitions of what it means to be absolute in, I believe, the next slide. But that just means that we do not have any values that can be any lower than this 1 point. So this is the absolute lowest that this graph can go. All right, here's a few more examples. So this is a graph of x cubed. You notice that this goes down to negative infinity and up to positive infinity. So we don't consider infinities to be a maximum or a minimum because infinity is not a number. So x cubed doesn't have any absolute maxima or minima. So it has no extrema, no absolute extrema. This is 1 over x squared plus 1. You see that this does, in fact, have a maximum right here. And since there is no value at any point greater than this 1 point right here, this is an absolute maximum. And then we also have this idea of like cosine or even sine. You have a maximum here, a minimum here, and here. And if you continue, we know that this is a periodic function that goes on forever. And so you actually have absolute maxima at every point that's starting here and adding 2 pi, which is the period of a cosine function. Because there is no point greater than 1, but there's a lot of points that do have the absolute maximum of 1. There are infinitely many absolute maximums because this goes on infinitely long, but this is the absolute maximum and this is the absolute minimum. All right, a few more examples. So we can have an idea of like a piecewise function having an absolute maximum or an absolute minimum. And here we're getting into the idea of a bounded function. So you notice in these functions here, these are unbounded functions, which means they go on, their domains are negative infinity to positive infinity. But here we have this idea of a bounded function, which means that we have a distinct start and stop, or at least one of them starts somewhere and stops somewhere. Maybe one of them does go to infinity, but these will be bounded, as you can see. And so when we're considering bounded functions, we do have to consider the endpoints because those may be part of the absolute minimum or maximum category. And we see that happening right here. So where we start is at 2 here, and we notice that that is the absolute highest point of this graph. So the boundary, the left boundary, is actually going to be the highest point of the graph. This is going to be the absolute maximum. We notice the absolute minimum is not the other endpoint. It is just some random point associated with this left-hand side of the piecewise function, right down here at -2. Here's another graph. This is just of some parabola, except that we have kind of chopped off some of the sides. We notice that it has an absolute minimum down here. It's not one of the endpoints, but we do have an absolute maximum of a piecewise function because we've now truncated it. We've created boundaries on it, and we do have an absolute maximum at 4 now. Same idea here. So this is of this graph here where we start at 0, But as we know, at x equals 2, this is a vertical asymptote. So this goes on to infinity. So there's actually not going to be an absolute maximum because it's infinity, and we can't call infinity a number. So there's no absolute maximum, but we do, in fact, have an absolute minimum right here at 0. So let's go ahead and start getting some formal definitions. So if f is defined over some interval, again, this means c in I, c in some interval, we say that f has an absolute maximum on I at c if f of c is greater than f of x for all x in I. So that means if your y value at c is greater than all y values everywhere else for all of your x, then it's an absolute maximum, which is exactly what we discussed, right? If your y value here is greater than everything else, that's the absolute maximum. That's what this is saying. Same idea for the minimum, but just kind of the opposite inequality sign. So absolute minimum on I at C if f of c is less than or equal to all f of x's. So your y value at some point c is less than or equal to all other y values that you have on your function for all x values. And we just say for f to have an absolute maximum or an absolute minimum, this is the absolute extrema. Okay, so this is called the extreme value theorem. I don't think that I'm ever really going to use that like terminology, but we do need to know this idea. So if f is continuous over the closed bounded interval, then there is a point at which f has an absolute maximum and a point at which f has an absolute minimum. So I could highlight this, but all of this is just pretty important. So kind of understand all of this. If it is closed and bounded, there is 100% an absolute maximum and an absolute minimum. And we will have to find that. Now, I want to note these can occur at the endpoints, but it can also occur at other points. So it can just have some random maximum that is not an endpoint, but would be the absolute maximum. And same with a minimum. All right, so we're just I'm going to spit a bunch of definitions at you and then we'll do some examples. So here, this is a very important definition. So we say that, so here, interior point just means that we're inside of our interval. So we don't necessarily have to recall this as part of the definition. We say that f is a critical number. So this terminology is very important. Of f if f prime of c is 0. So if your first derivative is 0, then that is a critical number. Or if it's undefined. We call the point cf of c a critical point. Sometimes we also say critical point even if we don't have the y value. Note that these two terms are interchangeably used. So I can ask for a critical number or a critical point, and I'm asking for the same thing. Typically, I'll say, if I do say critical point and I don't want a y value, I'll just say, what's the critical point? X equals what? And then we'll find the value. But this is a very important idea. Take the derivative, set it equal to 0, which is something we've been doing the entire semester so far. And that now we have a name for, that is a critical number. All right, now we have local maximums and local minimums. So what we notice is that we've changed the terminology. So instead of absolute, we now are talking about local. So f has a local maximum at c if there exists some open interval containing c such that f of c is greater than f of x for all x in some interval. And so I'm going to give you a quick sketch. I probably have some quick sketches or some drawings a little bit after this. So what this means is if you can create an interval, so this is not the entire function, this is not the entire bounded function that you have. I can say right here is a function. As you can see, this is an infinite function, so this doesn't have an absolute maximum or minimum. But if I kind of chop off the function here and here and create my own interval, I see that it does actually have a local maximum. So this is the local max. And if I chop off the function, say here to here, I see that right here would be a local min. And so anything that resembles a maximum or a minimum, but is not the absolute maximum or minimum, is what I would define as a local maximum or a local minimum, if you would like to think about it like that. So same definition of local minimum. If you kind of create your own interval, then your y value at that point is less than the other x values in that interval that you've created. And we will call kind of the combination of the maximums and the minimums the local extrema. All right. So again, this is kind of what I mentioned. This is a drawing, but way better than mine because I'm bad at drawing. So we see if we're looking at, we would typically want to consider all absolute and local extrema. So we see that this function goes down. We should have arrows at the end of each of them. It goes down to negative infinity. So there won't be any absolute minimum. But we do see right here, we have an absolute maximum. So this will be the absolute maximum. And now we can also consider that we have these turning points right here. Now, they're not any absolute anything, but they will be local. Because if we consider just this interval right here, then this point here is a local maximum. And if we consider, say, this interval here, then this point here is a local minimum. And in fact, if you were to take the derivative of this function, if you actually knew the equation of it, you would get 1, 2, 3 points where f prime of c would be 0. If you recall, this is what's called a cusp. So this is undefined. This does not have a slope equal to 0 because it doesn't have the left-hand limit equal to the right-hand limit, but these two would. All right, this is Fermat's theorem. Fermat was a very famous mathematician and kind of a jack of all trades. He knew a lot of things. He has had some very famous theorems. He did a lot of work in number theory. You don't necessarily need to remember that this is Fermat's theorem. He has a lot of important theorems. If you do take other courses, there's Fermat's little theorem. There's a lot of really important things. But this is his theorem in terms of calculus. It says if f has a local extremum at c and f is differentiable at c, then the derivative is 0. So this is pretty important to remember, but it also just kind of feels natural, right? If you have some local extremum and it's differentiable, then you're going to have a slope of 0. So to be differentiable means the left-hand limit has to be equal to the right-hand limit, which means that you kind of have a slow curve coming up to a maximum or a minimum, which means that you're going to have a horizontal tangent line, which has a slope of 0. Okay. So here are a few other examples. So here we see we do have a maximum. This right here, we don't know what the rest of the graph looks like, but if we assume this is the whole graph, this is going to be an absolute maximum. This is going to have a horizontal tangent line slope equal to 0. This here we see is like a little cusp. So we don't have it equal to 0 because the limits won't be equal, so it's undefined. Same here, this is going to be an absolute value function, so it's going to be undefined. This here does have a horizontal tangent or horizontal line equal to 0, but it's not a tangent line, so we don't consider it an extremum value, and we'll get to how exactly we're going to show that this isn't a maximum or a minimum very soon. And then this right here is undefined. So this is actually a vertical tangent line that we'll see in, say, like a cube root of x function, where it does have a vertical tangent line, but it's not going to be a vertical asymptote, and your derivative is undefined, but your function is defined there. Okay, so let's go ahead and find some critical points of some functions. Let's see, let me get a pen. All right, so to find the critical points of a function, what we want to do is take a derivative, set it equal to 0, and solve. So for a, f prime of x equals 3 times 1/3 is just 1, so I'll just write x squared minus 5/2 times 2 is just 5x squared plus the derivative of 4x is just 4. And we want this equal to 0. So what we can do, oh, I did not mean to write 5x squared because we have to subtract 1 from the exponent, so it's just 5x. This is where I say I was just testing you and hopefully you noticed. Now we want to factor this because this is just a typical quadratic equation. So we need two numbers that multiply 4 and add or subtract the -5. And what we can see is we can do -4 and -1. So we do x minus 1, x minus 4 equals 0. And we'll get x equals 1 and x equals 4. So these 2 points right here are going to be critical points of A. Let's look at B. So B, we already have it in factored form. And when we take the derivative, it should work out pretty nicely. We don't have to do quite as much. So f prime of x equals, well, we will have to use chain rule here. So this is 3, keep the inside. Oop, I just said keep the inside and I wrote the wrong thing. So keep the inside the same, which is x squared minus 1, subtract 1 from the exponent, which is 2. But then we have to multiply by the derivative of the inside function, so that's just going to be 2x. We need the first derivative equal to 0. So we can divide both sides by 3. That doesn't change anything, which means that this has to be equal to 0 and this has to be equal to 0. I'm going to rewrite this before I actually go ahead and set it equal to 0. X squared minus 1 is the difference of perfect squares. So this is x minus 1, x plus 1, and then I could divide the 2 out and just keep an x, because 0 divided by 2 is 0. Equals 0, which tells us that x equals 1, x equals -1, and x equals 0. So here we have 3 critical points or critical numbers. And at these points, we may or may not have a local max or min. All right, last one, we have C. We have a fraction now. So we have f prime of x equals, we have to use the quotient rule, obviously. Now, typically, I would say don't simplify. Don't simplify your quotient rule, leave it as is. But because we have to solve this, we will need to simplify our quotient rule. So the quotient rule is low d high. So low is 1 plus x squared. D high, derivative of 4x is just 4. Minus high, which is 4x. D low, derivative of 1 plus x squared is just 2x. Over low squared, which is 1 plus x squared squared. Now I'll go ahead and simplify my numerator. Before I set it equal to 0, it'll just really help if we simplify the numerator a little bit. And if you multiply this out and subtract it, I'll just give you that it is 4 minus 4x squared over our denominator, which is 1 plus x squared squared. If you tried factoring out the 4, there's nothing you can do to cancel. So we'll set this equal to 0 and we'll solve. There's no time where this would be equal to 0 in our denominator, so we don't have an issue there. That wouldn't be a critical point or anything like that. So we can multiply this to the other side, but multiplying that would just give us 0. So what this tells us is that 4 minus 4x squared equals 0. And if you move this over, divide by 4, square root, do the whole shebang, what we actually get is that x equals, and if you do solve it like that instead of factoring and doing it like that, you have to remember that when you take a square root, you take the plus or the minus. Because here you actually get 2 values. You could get the x is 1 and x is -1. So those would be the critical points here. So whether or not a maximum or a minimum exists, even if your derivative would be kind of funky looking, that would still be considered a critical point. All right. Here's another theorem. This is the location of absolute extrema. I'm not going to refer to this by name again. I'm also not going to highlight it because this is something that we should just write down the whole thing. Let f be a continuous function over a closed bounded interval I. So say maybe it goes from A to B. The absolute maximum of f over I and the absolute minimum of f over I must occur at the endpoints of I or at the critical points of f in I. So that's kind of what I was explaining earlier, where I said either it happens at the endpoints or it'll happen at a maximum or a minimum that just kind of would naturally occur in the function. So these are the really important parts. Either it occurs at the endpoints or the critical points. So if you're given a closed bounded interval, what you'll have to do to figure out what the maximum and the minimums are for the absolute max and mins, you'll have to figure out what the values will be at the endpoints. And by values, I mean y values. Find the y value endpoints, and then find if there's any maximums or minimums. that would give you some absolute value as well. And you'll compare those values to see which is the highest one and which is the lowest one. All right. And so that's just kind of what this is saying here. So it's saying evaluate f at the endpoints a and b, given that this is a closed bounded interval. Once you evaluate f at a and b, that's just simply doing f at a and f at b, just plugging it in, no derivatives, very simple, straightforward plug in. Next step is we want to find all critical values in a to b and evaluate f at those critical points. So what we were just doing was finding the x values. We didn't find any y values, but now we're going to want to find the y values associated with those x values. After you find that, you're going to compare the values from 1 and 2, and then the absolute extremum must occur at either the endpoints or the critical points. So therefore, the largest of these values is the maximum, and the smallest of these values is the minimum, which feels pretty intuitive. So let's go ahead and practice. All right, this will be the last slide for today. So this won't be a particularly long video, but it's a very, very important video. Again, make sure that you know this because the next couple of lectures that we do are kind of just going to build upon this idea. So if you're feeling a little bit shaky about this, definitely spend a little bit more time practicing this, maybe do the homework questions that are on this, and understand this because we're going to be just adding to this over the next couple of lecture videos. So we have two examples. For each of the following functions, find the absolute maximum and absolute minimum over the specified interval and state where those values occur. Anytime you see a question where it says state where those values occur, this is specifically also if you were to see a homework question where it says find the values, the word values means y values. So it would tell you like find the x values if it wanted that. If it just says values, it's talking about the y. So first of all, what we're going to want to do for this function is plug in the endpoints and find what those values are, and then we'll deal with the derivative and everything after that. So since we're from 1 to 3, we'll say f of 1 equals negative, and then we'll just plug it in. Negative 1 squared plus 3 times 1 minus 2. Well, 1 squared is 1, so that's negative 1 plus 3 is negative 2, minus 2 is negative 4. Now f at 3 is, let's see here. Oh, I wrote that wrong, didn't I? I was like, I feel like this is off. That's because it is. Trust your gut. You know, I could do calculus. I never said that I could do basic addition and subtraction. Negative 1 plus 3 is positive 2. Positive 2 minus 2 is 0. Well, now that we know that I can do that. Okay, now we can move on. Check your work, folks. I can do calculus. I can do most upper level math. Man, addition's tough. All right. Now plug in 3. So we get negative 3 squared plus 3 times 3 minus 2. So this is 3 squared is 9. This is negative 9 plus 9. That goes to 0. Minus 2. That's just negative 2. And I do know that's correct. Okay. Now we have, these are the values of the boundary points. We can go ahead and find the derivative. F prime of x equals negative 2x plus 3. So we can say negative 2x plus 3 equals 0. Subtract the 3, divide by 2, we get that x is equal to 3 halves. But we're not looking for the x value, we're looking for the y value. So we will find f, specifically f. So you might be inclined to plug this back into our f prime, but if you do that, you're just going to get 0. So it's very important that once you find your x value, this tells you that most likely you're going to have a maximum, minimum, or just something weird happening. This is your critical point. You have to plug that back into your original function. So f at 3 halves is negative 3 halves squared plus 3 times 3 halves minus 2, which is, I will just give you the answer to be 1/4. So now what we have to do is we need to compare all of our y values and figure out what the absolute maximum and the absolute minimum are. So we have 0, negative 2, and 1/4. So the absolute max is going to be the highest value, which is 1/4. So I'll give it to you in coordinates. So this is 3/2, 1/4. And the absolute minimum, you could also just write it as 1/4 because we are being asked for the value. The absolute minimum occurs at -2, so that's 3, -2. All right, let's take a look at this one, and we'll do the same exact thing. So first we want to plug in our boundary points. I'm going to try really hard to make sure I plug these in correctly this time. Apparently, I have not had enough coffee today. Okay. G at 1 is 1 squared minus 4 times 1 plus 3. 1 minus 4 is -3 plus 3 is 0. G at 4 is 4 squared minus 4 times 4 plus 3. I swear it won't cancel out like that all the time. For some reason, the two examples I have just cancel out. 16 minus 16 is 0, plus 3 is 3. Now we can take a derivative. So g prime of x equals 2x minus 4. If we set that equal to 0, add the 4 over, divided by 2, we get that x is equal to 2. So we could take 2 and figure out what is the y value at 2. So we need g of 2, again, not g prime of 2, because we'll get 0. So g of 2 is 2 squared minus 4 times 2 plus 3. So that's 4 minus 8, which is -4, plus 3, which is -1. So we have 1, 2, 3 y values to compare. Let's look at the absolute maximum. So the absolute maximum is going to occur right here at 3. You can write it in a coordinate, but because it specifies values, you might just want to say 3 because that is the y value that we're looking at. And the absolute minimum occurs at -1. All right, so these concepts, again, are very important. It's very important to understand that we get maxes and mins from taking the derivative, setting it equal to 0, and solving. And we're going to understand in the next couple of lectures how, given that information, to actually figure out if it's a maximum or a minimum. All right, as always, if you have any questions, let me know, and I'll see you next time.